Tree-based learning architectures are the foundational building blocks for many of the most effective machine learning techniques used in industry today. The algorithm begins at the root node, the top-level container housing the undivided dataset. Data then flows into decision nodes, intermediate steps where the algorithm evaluates samples against specific criteria. The process terminates at leaf nodes, representing the final predicted classification. In modeling libraries like scikit-learn, every node is programmed to split into exactly 2 child nodes. This 2-level binary split is functionally equivalent to a single-level 3-way split, but it significantly reduces the computational demand on the system. To manage these splits, the model operates as a greedy algorithm. It does not plan the entire architecture in advance. Instead, it looks only at the current node to find the immediate, most optimal split. To see how the algorithm identifies that optimum, we need to look past the high-level structure and manually execute the underlying math. This execution follows 2 phases. First, the algorithm generates a list of every possible candidate split, and second, it scores those candidates against a mathematical objective function. The model does not make holistic judgments. It uses recursive binary partitioning to systematically sort data into specific categories. We can track this using a classification dataset with 3 features: the target variable of fruit type, a categorical variable for color, and a continuous variable for diameter in centimeters. The algorithm evaluates the categorical variable first, isolating the color column to identify potential split points. Because the splits must be binary, the algorithm tests each individual category against the rest of the group using yes-no logic. For example, it generates a candidate split for is color red, where all yes samples move to the left branch and all no samples move to the right. Shifting to the continuous diameter variable requires a different mechanistic approach to generate candidate thresholds. The algorithm starts by sorting all numerical values in the column in strictly ascending order. Once sorted, the algorithm identifies every consecutive pair of values throughout the range. It then calculates the mean of each pair, establishing the exact numerical thresholds the model will test. These 6 means, combined with the categorical color splits, provide the full pool of candidate splits for this node. By sorting and averaging the raw data, the algorithm converts a range of numbers into a finite list of testable binary conditions. With 9 potential candidate splits now identified, the algorithm needs a metric to determine which one separates the target classes most effectively. It measures this effectiveness using impurity, the degree of mixture between the target classes within a node. A node is perfectly pure if it contains only one class. The highest possible impurity occurs when a node contains an equal number of each class. To quantify these states, scikit-learn uses a metric called Gini impurity. In this formula, P of I represents the simple probability of a sample belonging to a specific class within that node. We can test this on our first candidate, is color red, by calculating the impurity of its 2 resulting child nodes. The left child node contains 3 samples. To find its Gini score, we subtract the squared probabilities of each fruit type. We have 1 apple out of 3 total samples, and 2 grapes out of 3. Squaring those fractions and completing the subtraction gives the left node an impurity score of 0.445. For the right child node, we have 4 samples, 3 apples and 1 grape. We square the probabilities of 3/4 and 1/4. This results in an impurity score of 0.375 for the right node. We have quantified the mixture in both nodes, but to evaluate the split as a single unit, we have to combine these scores. We cannot simply average the 2 Gini scores of 0.445 and 0.375. That would ignore the fact that the 2 nodes represent different amounts of data. The left node has 3 samples, while the right has 4. Instead, the algorithm calculates a weighted average, scaling each node's impurity by the fraction of the total dataset it contains. We multiply the left node's impurity by 3/7, its proportion of the total fruit. Then we multiply the right node's impurity by its larger share, 4/7 of the dataset. Adding these together gives a total weighted impurity for split A of 0.405. The algorithm performs this exact calculation for all 9 candidate splits we identified earlier. When we compare the results, split A is roughly in the middle. Split C is the least effective at 0.486, while split E is the clear optimum at 0.229. Since the goal is to reach the lowest possible impurity, the algorithm selects split E to partition the root node. By using this mathematical proof, the decision tree identifies the statistically superior threshold without relying on human bias. The algorithm enters a recursive loop. If a resulting node is pure, with a Gini score of 0, it becomes a leaf node and stops. If a node is still impure, the algorithm starts the process over, generating new candidates and scoring them specifically for that subset of samples. This architecture provides several practical benefits, particularly during the data preparation phase. Because the model identifies split points through relative sorting rather than absolute values, it is inherently resistant to extreme numerical outliers. This reliance on rank order thresholds also removes the need for data normalization or scaling before you begin training. However, there are significant trade-offs. Testing every possible threshold across every feature is computationally intensive, particularly as the number of dimensions in your data increases. Decision trees are also sensitive to variance. Small changes in the training data can lead to entirely different thresholds, resulting in a significantly altered final tree. Because of this sensitivity, individual decision trees are rarely used by themselves in high-stakes environments. Despite those limitations, mastering this calculation is the first step toward understanding ensemble models like random forests and gradient boosting, which use these individual decision trees as their fundamental building blocks.